Rotation of the motors causes thrust, and the thrust that overcomes the gravity causes the drone rise upward. If the thrust and gravity are even, the drone flies horizontally. Decreasing the thrust, it descends downward. By controlling the thrust, you can fly the drone upward or downward. Let's think about hovering the drone 1 meter height. By now, the drone is not flying. To make it start, you increase the thrust. You can slide the throttle key up, drone starts flying upward. Sliding down the key will make the drone descend down. If you slide up the throttle key excessively, drone will pass the target and fly far from it. You should decrease the thrust. If you slide down the throttle too much, in this case, drone falls so fast and may plummet to the ground. Excessive throttle key handling, you will never get hovering at the desired position. To make it hover at the target altitude, you need to increase the thrust much at the beginning for the drone to take off. However, around half a meter height, you have to decrease the thrust in order to make it stay around the target altitude. If you do not decrease the thrust, drone will fly over the target. You can say that with this acceleration, drone will never stop and pass off the target altitude in a second. Let's do it again. Throttle up some large amount to take off. Decrease the throttle around half a meter and reduce the acceleration. Once the drone reaches around the target altitude, you control the throttle with a small amount. And finally, drone hovers at the target altitude. If you close your eyes, you cannot hover the drone at the target altitude. Your eyes are sensors, your hands are controller. How much you slide the key determines the sensitivity of the flight. This is how the PID controller works. Inertial measurement unit is the eyes, seeing the current state, and rotation of the motors determines the thrust. The controller's input is the target state, and output is the RPM of the motors. Inertial measurement unit inside the drone reports its states to the PID controller. PID controller calculates the output from the difference between the target state and current state, and command the thrust to the motors of the drone. And this automatic PID loop runs 2000 to 8000 times per second continuously. Let's dive into PID. In PID controller, output is controlled by P, I, and D terms. Mathematically, P term is proportional to the error. I term is the integral of the past error. D term is the derivative of the error. P term and D term have close relations with the drone hovering, and let's focus on the P and D terms. P term is target altitude minus current altitude and multiplied by Kp parameter. D term is target velocity minus current velocity and multiplied by Kd parameter. In hovering drones, the target altitude is 1 meter and the target velocity is 0 meter per second. Let's see how the thrust can be controlled only by P term. Here, both the altitude z and the velocity z dot is increasing. The output thrust is decreasing. In the second stage, z is increasing while z dot is decreasing. The output thrust is still decreasing. However, decreasing D term will be able to alleviate the rapid drop of the thrust. This is third stage. Here, z is declining and z dot is also decreasing. In the fourth stage, P term is increasing but D term is decreasing. D term can help alleviate the rise of the thrust. Let's see how the graph to be if D term is activated. Here you can see mild decreasing and mild increasing of the thrust. This is the PID simulator. It shows how the monocopter hovers at the target altitude. Here you can control P, I, and D values and see how the copter hovers as if it real flies. It looks perfect. However, does it really work on the real world? Of course it works, because there are real drones which use this PID. However, I want to verify this with real-world hardwares, using motors, props, and flight controllers. I decided to make a monocopter, and it flies up and down by the PID in-flight controller. Two probes are better, because they provide more thrust and prevent the drone from rotating. A transparent acrylic tube will keep the copter fly just up and down along Z-axis without going outside. We need a distance sensor to measure Z distance from the base. A Bluetooth serial is used for communicating with my Mac PC. Flight controller can be Arduino or small STM32. If there are only P value, controller works as P controller. Let's see how P controller works. P controller doesn't make drone hovering, just going up and down. If we increase D value a little bit, controller works as PD controller. Let's see how PD works. It eventually goes to hover state, but it takes so long. How about increase D value a little bit more? Yes, it hovers in a short time. Let's increase D a little bit more. Yeah, it hovers right away. Now we covered how D values affect the flight controller. Now we compare the flight in one graph. We observe D value from 0 to 6 increasing by 2. It is proved that PID works great in real drone world. This small project combines hardware and software, including embedded firmware and Python as control window. There inside is a brief protocol to communicate from drone to PC. I hope this helps the people who are interested in drones and who are going to understand flight.